Today we are going to look at Kirchhoff's laws. Now the first law, it's actually the fundamentals of it are very simple. The two laws are simply coming from fundamental conservation laws, the conservation of charge and conservation of energy. So if you understand the concept behind it, it's easy. So series circuit, parallel circuit, you know what they are. Kirchhoff's first law says like this: the sum of the currents entering a junction in a circuit is always equal to the sum of the current leaving it. That looks pretty much obvious, but that is Kirchhoff's first law. Maybe when they were trying to find it for the first time, it was difficult. So you already know conservation of energy, and you already know conservation of mass, and you already know conservation of momentum. Now there is another concept, the conservation of charge. Now if you look at particles in chemistry and in atomic physics, which you have learned in IGCSE, we denote particles using the two numbers, the nucleon number and the proton number, the atomic number and the mass number and the atomic number. So if you take a proton, we denote it like P. A proton is denoted with P plus 1, right? A neutron is denoted with naught 1. An electron is denoted with -1 naught. So its mass is negligibly small. Its mass is okay, but its charge is 0, and a proton has mass 1 and charge 1. So these three people, the three building blocks of the material life, are defined using these two things. So one is an indicator of mass, the other is an indicator of charge. And what does it tell you is that, of course, you know mass is an important thing in life, in existence, but equally comes the charge. And it is based on mass and charge, everything is characterized. The fundamental particles, thus the atoms, the molecules, the elements to the universe. So just like how mass is conserved, the charge should be conserved as well. So that is what illustrated by Kirchhoff's first law. Now I know that as scary as the name sounds, the law is not that scary. But there can be a certain, not a certain issue, like when you're doing the next example you might find it out. But for the time being, it is very simple. If there is a current is coming, it gets split into 3, then it should add up. I is equal to I1 plus I2 plus I3. So the fact that the current does not get used up at a junction is because current is the rate of flow of charge, and charges cannot accumulate or get used up at a junction. So one thing that is beautiful here is not only they are talking about used up, even if charges are getting accumulated somewhere. So in a circuit, charges leave the battery. Charges leave the battery, but if they haven't reached the resistor and they somehow hiding somewhere, then that is accumulation of charges. Just like black money, there would be black charges. Charges would accumulate, but fortunately there is nothing like that can happen, because now the force is going to be throughout the wire, and throughout the wire it's going to drive you. It's like this. The battery is like your command room, sixth form command room, and when the bell rings, a teacher should come and drive you out of the command room to your lessons. Unfortunately, like there are students who gets accumulated in the corridor. They hide, and they hide behind walls, and they get accumulated, and they try to skip going through the lamp, the enlightening lesson. It is possible in the setup of the corridors, but it's not possible in the setup of an electric circuit, because the teacher is, in the case of an electric circuit, the teacher in the battery is not just there in the common room. The force is going to act throughout the field. It's like the teacher is capable of like looking at you and shouting at you from the common room itself. So it's like the field extends. It is not that he has to chase you behind, but he's somehow able to monitor you and shout at you to go to the lesson, from even if you're hiding somewhere in a sacred place. Even if you open up the locker and somehow shrink yourself into it, still the field is going to act and drive you. So there's no way a charge can hide like a student. There's no way a charge can accumulate. The force is going to be there, and the force will drive you throughout. It will hold your hand and pull you from the positive terminal to the negative terminal. So the thing is, unlike the conservation of charge, where we're simply talking about charge being created or destroyed, unlike the conservation of mass, where we are talking about mass being created or destroyed, here there is no such need to talk, because there is another option of accumulation. But we are closing both the doors, not used up and not accumulated. So both possibilities are there, and both are impossibilities. Mission impossible. So simply there is no way. It's like life and death. If you are born, you are bound to die someday or the other. If a charge leaves the positive terminal, there is no other way than it reaching the negative terminal, like it or not. And sum it up in Kirchhoff's first law. Just one funny question for you to think about. If you had to consider the classrooms, the labs and the rooms as different components, bulb, resistors, and if you had to consider the corridors and the staircases as wires, is it a fair comparison? why is it like why is it better to consider the corridor the wire rather than the classrooms the wires? Just think.